So we have Saul Teukolsky speaking to us now. He's a professor, I don't know how you do this, both at Cornell and at Caltech. And he's known for his work in numerical relativity, of which he was a pioneer, namely using supercomputers to solve Einstein's equations to allow for predictions for LIGO, LISA, and the gravitational wave experiments. So, Saul.
As you all know, we are living through a revolutionary period in gravitational physics, prompted by the LIGO detection starting in 2015. What many of you may not realize is that there is a parallel revolution going on in gravitational theory that's being driven largely by our ability now to solve Einstein's equations with high precision for very complicated situations using big computers. And what I want to talk about today is one such application of this recent ability. So when two black holes spiral together, losing energy to gravitational waves, this is a picture that I took from Kip Thorne's popular book. This was drawn before we knew how to solve Einstein's equations numerically. You can see in the middle region there, Kip has marked the merger supercomputer. That was wishful thinking those days. What I want to talk about today is to focus on the last section. After the black holes merge, they form a single black hole that's settling down to equilibrium, oscillating and emitting, losing energy through gravitational waves. And you'll notice Kip marked that as known. And that's because, like good physicists, if you have a situation that's close to equilibrium, we all know you can use linear perturbation theory. And in fact, that was my thesis a little while ago. Was to figure out the formalism to be able to do that calculation. Now, if this was some kind of freshman physics course, we would talk about the normal modes of oscillation. These oscillations, though, are so highly damped, the damping time and the frequency are comparable. And as a result, we've given these the name quasi-normal modes. So that's what I'm going to be talking about. Now, the no-hair theorem in general relativity says that an equilibrium isolated black hole is described by a unique solution of Einstein's equations, the Kerr metric. And therefore, an astrophysical black hole will only need two numbers to determine it, the mass and the angular momentum. Before someone says, what about the charge? Right? In astrophysics, you don't expect to find a strongly charged object. There's always plasma around that will neutralize that. So we'll ignore that. Right? So this is the famous saying due to Wheeler, a black hole has no hair. Wheeler, of course, as you may remember, was completely bald. So the quasi-normal modes, the frequency and the damping time, therefore, should depend just on these two numbers. Right? And since we can apply the perturbation theory to do this, one can actually calculate essentially analytically. Right? You actually have to solve a root finding problem, but if you've worked on trying to solve Einstein's equations on a big computer, then root finding is considered analytic. All right, this is not necessarily true in alternative theories, right? Black holes can have hair. So there's been some interest, therefore, in the community to ask questions like, can we actually test from LIGO-like or future gravitational wave detections, can we test this ring down part of the signal and see whether the modes are consistent with depending on only two numbers? All right, so here's all you have to know about doing Kerr perturbation theory. well, at least for the purposes of this talk, right? So at late times, H, which is the gravitational wave strain, the delta L over L in the detector, is a superposition of these quasi-normal modes. And at late times and large distances, you'll see that the dependence is just on this T minus R star. You can forget about why the star is there. That's because we're on a curved background, but it's really just the outgoing wave. And then there's an angular dependence, this function S, that depends on the angular coordinate. Here, I've switched to the notation A. It's just the angular momentum parameter in the curve. And again, for the purposes of this talk, we don't need, these are spin-weighted spheroidal harmonics, but the LIGO people detect things, express their things in terms of modes, in spherical, spin-weighted spherical harmonics. And you can just transform these to these, and we know how to do that now. So I'm just going to gloss over that. You can think of this as just spherical modes. Okay, so the modes then at late times and fixed large distance just are these damped sinusoids, right? There's some real part of the frequency here, and then the imaginary part of omega gives the damping. All right, so the L and M are the angular modes, and then the N comes from a radial eigenvalue equation. It's just like quantum mechanics with barrier penetration. So N is called the overtone index, which turns out to be a terrible name, because when you think about overtones from music or something like that, you think of subdominant modes that are harmonics of each other. Well, for black holes, the overtones are neither subdominant, as we'll see, nor are they harmonics. Right, so N is just a way of labeling the different modes. The N equal to 0 is the fundamental, and it's the least damped. N equal 1 is the next most least damped, and so on. Now, the reason this is a terrible name is that the community has just ignored them, right? Because everyone knows overtones are subdominant. Well, so. Now, back in 2007, Alessandro Bonanno, who you'll be hearing from tomorrow, working with Greg Cook and Franz Pretorius. Now, by the way, 2007, as far as numerical relativity is concerned, that's the Stone Age. The very primitive computers, barely able to get accurate results and so on. And they did a simulation of the merger of two equal mass black holes. And they found that when they analyzed the ring down part of the signal, they could actually fit the 2-2 is the dominant quadrupole mode, the fundamental, n equal to 0, and actually found 3 overtones, n equal 1, 2, and 3, were present in the signal. And this was a good fit to the signal, even close to the peak amplitude of H. Now, naively, you might, well, not naively, everybody thought that the peak of the waveform, right, that's where the signal is strongest, that must correspond to the most nonlinear part of the merger. How could a linear perturbation theory treatment be a good approximation? Anyway, nevertheless, especially Alessandra and her collaborators worked on the effective one-body model, which is a semi-analytic waveform model, which is very widely used in the LIGO data fitting, through parameter estimation. And so they used some of this insight in fitting the late part of the wave. And the feeling developed in the community, who they don't read papers, who can keep up with all the papers, right? They read the abstract at best. The feeling developed that these quasi-normal modes being present near the peak, well, that was okay for data fitting. you have enough parameters, you can fit the data and so on. But everybody still thought that the wave was very nonlinear at the biggest signals. So the question then arose, when does linear perturbation theory really become applicable? In other words, here's the envelope of the wave, right? If t equal to 0 is the maximum amplitude, these are just the two polarization states. How long do you have to wait before linear perturbation theory, a superposition of these normal, quasi-normal modes, is really applicable? And in 2020, one of my graduate students, Matt Giesler, right, this is why young people make discoveries, right? They don't know what they're supposed to think. So, Matt just decided he'd been to a talk about this, when is this a good approximation? He said, I can solve this problem, right? He was working on doing numerical simulations. So he went and just tried different start times and found that you really can get a good fit from essentially close to the maximum here on. And so here's what he did. So you're looking, just say, at the 2-2 mode, right, which according to this is some superposition, which you'll cut off at some capital N, right? So these omegas are known by the no-hair theorem. You know from this is, by the way, numerical, high accuracy numerical wave, the kind of thing you can do these days, right? So there's essentially, so the omegas are known because you know the final mass and spin of the remnant. Measure that in your simulation. So it's just linear least squares. You fit for some complex amplitudes. And as you increase the number of terms you keep in this sum, this is a plot of the mismatch it's just doing an overlap integral between the numerical relativity waveform and the fit, and then subtracting from 1, so small is good. And you can see the fit gets better and better, and you can go all the way to 0 is at the peak. Okay, so down here to a level below 10 to the minus 6. Well, that's pretty surprising. So what this is saying is, so this is just a plot of these of this overtone decomposition, right? So here's the fundamental, most long-lived, and then you add all these overtones, right? So you can see at the peak, fundamental is subdominant. These are bigger, but they just decay more rapidly. Okay, in fact, this becomes dominant at 10 m. The light crossing time is measured is just proportional to the mass of the system. And if you put that in real time for the first gravitational wave detection by LIGO, that's 3 milliseconds. And that's exactly where, if you go and look at their paper, they did a test looking, they could only measure the fundamental and had to wait 3 milliseconds after the peak to be able to see it. All right, so what this is suggesting is that the early part is dominated by the overtones and not by nonlinearities. How else could you check this idea? Well, another thing you can do is you could say, is it just because I've got so many parameters in the fit, right? I'm just overfitting to the data. So what Matt did was varied those frequencies by making just random small perturbations to them and redoing the fit. And he found that any perturbation made the fit worse. All right, so that at least is some evidence that there's something real going on here. And this, of course, caused controversy in the community. People said this can't be right. And there were some mathematical people who jumped in and made some arguments. Well, those were wrong. They were not applicable. to this case. So how would you really try to confirm that the overtones are really there? Well, one thing you can do is you can imagine doing the fit starting at the peak. Right, so let's take this to be the peak time. And then repeat the fit, keeping the same end time, but just moving your start time a little bit later. Right, and keep doing that. If the underlying signal really is a linear superposition of modes, you should get the same amplitudes, just with a correct exponential decay for the different start time. And similarly, the phases should be constant. All right, now suppose you actually did this test and you found different amplitudes. What would you conclude? Obviously, this is a trick question. Well, the point is, if you're a good physicist, there are two possible conclusions, right? One is, it's not really a linear superposition. The other possibility is that you did a bad job of doing the fitting. Okay, and what I want to show you is some very recent work. In fact, we'll have a paper probably next week on the archive, that it's the bad, everybody else was doing bad fitting. Okay. All right, so quick lesson on how to fit damped exponential. All right, the first thing that I'm sure I don't have to tell you, you all know this, right? If you need to fit an exponential, you try to avoid nonlinear least squares. Linear least squares is analytic. Okay, there's just a formula in linear algebra for doing. Nonlinear least squares, you're doing root finding, essentially. Okay. So the phase in that exponential is not a nonlinear parameter. You should rewrite that, pull out the phase, right? You can write it, if you want to do it in real numbers, you can do it with a cosine and a sine. But the amplitude and the phase are linear parameters when you fit exponential or trig function. Okay. However, the frequency is a nonlinear parameter. If you don't know the frequency ahead of time, you have to do nonlinear. Okay. Now, so the decision you have to make when you're doing the linear fitting here is, what modes do I include in the fit? Okay, and we'll see that's crucial. If the frequency is not known and you're going to do nonlinear least squares, this is an extremely ill-conditioned problem numerically. Ill-conditioned means you make small changes, small perturbations where you have a little noise in the problem. The results can change by a large amount. This has been known, from the days of isotopes, when people used Geiger counters, right, and things like that, try to fit with it. The earliest reference I could find is Lanchas had a little book that came out in 1956, where people were still doing, turning the crank on those old calculator type things, so on. Here's a chapter on this. And this, of course, has been rediscovered by physicists many times. Right. The best algorithm for doing this is not to go to Python and use SciPy's nonlinear least squares. It's terrible. The best algorithm has also been known for a long time, in fact, since 1973. It's called variable projection, and they even published a Fortran program called VARPRO to do this. And there are descendants of that program today, so I still call it VARPRO. All right, so let's look at this ill conditioning a little bit more carefully. So let's assume this is now just an analytic test, right? You could go home and do this yourself. So let's make a superposition of these particular modes, right? You can see the fundamental and some overtones, all analytic. And let's do linear least squares, where we vary the start time, the T0, right? And then we do, so the T0 is being fit from between 0 and 20, right? So say do 20 different choices, and we'll do the fit out to 80. So there's still some noise here, but it's at the level of 10 to the minus 16. Okay, that's the machine precision. Now repeating, so you can see you get perfect representation. Now add 10 to the minus 5 Gaussian noise. Okay, what happens? So even though the noise is at the level of 10 to the minus 5, you'll notice the stability, your ability to do the fitting, is lost at the level of 10 to the minus 2 or 10 to the minus 3. That's what we mean by ill conditioning. And that's just for the linear case. If you do the nonlinear case, so now I'm showing the complex frequency plane, we now use VARPRO, and we try to reproduce these frequencies, and even we'll do them one at a time, right? So if it's analytic, you can do it. You recover the frequencies that you put in. But if you add noise at the level of 10 to the minus 5, you'll see that the fundamental down here and the first overtone are fine. But then even starting here at n equal to 2, it starts wandering around. So this is an initial guess, and then VARPRO goes all over in the complex plane and can't even estimate the errors. And this is the issue here in trying to do this test. All right, so even when they're really there, it's hard to find them. So the new work I want to report is what you can do, this revolution I mentioned, when you have highly accurate waveforms. So what do I mean by highly accurate? All right, so here's a numerical waveform that's from a case that is close to the LIGO detection, right? And that's what it looks like. But that's wrong. Okay, and the reason it's wrong is because it's missing a piece. You see the end of the wave doesn't end at 0 strain. There's a net displacement here, right? And I've drawn the additional contribution that was missing here. And this is something that was only in the last 2 or 3 years that we've been able to do numerically, to actually track that memory contribution. And for the experts, this is Cauchy characteristic extraction. That's the technique that lets us. All right, so now finally I can connect to Steve Weinberg. Okay, this is a triangle that I think Andy Strominger popularized, right? There's 3 parts of theoretical physics that are connected. Soft gravitons or photons, going back to Steve's famous paper. Asymptotic symmetries and the memory effect. All right, and now I have to confess, I'm not going to talk about gravitons at all, right? I'm only going to talk about the bottom 2. All right, so I showed you what the memory effect is, right? So these are all connected, and they're connected to asymptotic symmetries. So the question is, I have a question for people in the audience. How many of you were taught that the gravitational wave strain is gauge invariant? Put your hand up. I was taught. Sue for malpractice. Okay. It's not. It's only gauge invariant for infinitesimal gauge transformations on a Minkowski background. And the transformations, if you make large transformations, not with an infinitesimal parameter, then you can make transformations that are not simply Lorentz transformations, but a bigger symmetry group called the Bondi-Metzner-Sachs group, the BMS group. Okay? So in order to analyze the late ring down carefully, you have to make BMS transformations that put your numerical waveform, which ends up in some random BMS frame, into the frame of the final black hole, right? That's a unique BMS frame. All right, so now if you do that, the fitting procedure is much easier. You can start at late times, identify the modes one at a time, going backwards, and check their stability. All right, so that these modes here, so this is after you've found all the modes, you do the entire thing, and you find that these will disappear. But these wouldn't have been added to your solution until you'd have added these one by one. And it turns out that with this technique, okay, so this is from the SXS catalog. This is a very accurate recent numerical waveform for a highly spinning case. And look at all the modes you can find. Right? So this is found by carefully analyzing and making sure there's at least some region of stability where the mode amplitudes are correctly defined. And not only that, you can see the results of second order perturbation theory. Right? There are some modes here where if you multiply two exponentials, right, you get beats. And so the frequencies are the sum or difference of these. And these would be nonlinearities, but not real nonlinearities, right? They're linear perturbation theory is still applicable. You're just going to second order. So whether LIGO will be able to, well, I don't think LIGO will ever see these, right? But future detectors like Cosmic Explorer or LISA, these would be very strong tests of general relativity. Okay, so to summarize, I think it's really true that the ring down, the linear perturbation theory representation of the wave does begin close to the peak strain. The overtones dominate the early ring down. Fitting can be tricky. You have to reduce the noise floor by doing all these various tricks. There are second order quasi-normal. Some second order quasi-normal modes had already been identified. The 2-2 plus 2-2 gives you a 4-4, but that would be relatively hard to detect. It's a higher mode. But these are nonlinearities in the 2-2 mode. And the true nonlinearities, meaning the failure of linear perturbation theory, seems to have a surprisingly small effect in the ring down, even close to the peak. Thank you.
So much, Saul. And it's time for some questions, comments, funny stories.
Hi, Saul. Thanks for the very nice talk. I didn't get the connection between the memory effect and these normal modes. Is there a connection, or were you just showing us that the numerical simulations are now good enough to get the memory effect and precise enough to do this normal mode analysis?
No, so the asymptotic symmetry group gives you, once you have a symmetry group, you can have conservation laws. So there's a balance law between the time dependence of the gravitational wave strain, basically, and fluxes. There are flux contributions, right, in this balance law that follow from just having the asymptotic symmetry group. And when you look at that balance law, it predicts, it can tell you, gives you information about the memory. It's a little technical. I don't have a way to explain it to you you know, in 30 seconds without a black hole.
We have time for.
Hi. So I was wondering, like, on the data analysis side of things, would this by any chance make it easier to sort of, because right now practically it can be hard.
So absolutely, absolutely, because from the data analysis point of view, if you have to wait too long after the peak of the signal, then your signal to noise is decaying exponentially. So the earlier you can look in the wave, and so already if you take the public data for 1509-14 and you repeat basically what LIGO did, but you try to look, you know, for not just the fundamental, but fundamental plus one overtone. So we showed roughly at the 20% level, there's the presence of the first overtone. It's not overwhelming evidence, but it's very suggestive that we won't have to wait for LISA or something, that as the detectors improve, we have a good chance of seeing these overtones. Yeah.
Okay, thanks.
Let's take one more question from.
Thanks, Saul, for the very nice talk. I was curious, with the improved fitting and the improved waveforms and the improved simulations, are you getting closer to kind of pinpointing where perturbation theory will fail? Because the thing that always disturbed me is you can be aggressive with these fits. You can go well before merger. You get a reasonably good fit to the waveform. So are you finding clearly where things break down?
So first of all, let me just say that you don't get such a great fit if you go too early. I mean, we were talking, I don't know if you saw the scale there. We were down to level 10 to the minus 8.
Yeah.
All right. So certainly we can see deviations. Even when you get close to the peak, you can start to see things turning. It's not great.
Yeah.
So I think you have to define the criteria.
Absolutely.
Are you happy at 10 to the minus 4? Right. And depending on where you set that determines it. So obviously, if you go back too far, right, you don't even have a common horizon yet. It seems to me silly to think that you're doing anything meaningful with linear perturbation theory.
So before merger, you would say that's probably where it certainly breaks down, but maybe
Right.
to merger?
But of course, this is all coordinate dependent, because what do we mean, right? You talking about where the horizons have merged, right? If it's the apparent horizon, you know, that's slicing dependent, right? How do you choose your time coordinate? You can change all of that. And how do you relate retard, right? You're observing something at infinity. So you have to talk about the retarded time. Well, that's not uniquely defined. So I don't know how to formulate these things precisely.
Thank you.